Hello everyone. A very good morning to all of you. I am Dr. Ameya Durve, and on behalf of Tri-Diagonal Solutions, I would like to welcome you all to today's webinar. Mixing tanks scale up your mixing processes like a pro. Before we get started, I would like to go over a few housekeeping items. You should see an attendee interface on your computer desktop in the upper right corner. You are listening in using your computer speaker system by default. If you would prefer using a telephone, you need to select telephone in the audio pane and you will get the dial-in information displayed on your screen. You will have the opportunity to submit the text questions to the presenter. Please type in your questions in the questions pane of the control panel. You can send in the questions at any time during the presentation. We'll collect all these questions and address them in the QA session towards the end of today's presentation. So before I actually give the handover to Dr. Kasat, I would like to introduce you all to Tri-Diagonal Solutions. Tri-Diagonal Solutions was founded in year 2006 by professionals from industry and national labs. With the motive behind Tri-Diagonal Solutions was to provide solutions to the process industry using modeling and simulations. Compute, innovate, develop has been our motive. We believe in performing computations and calculations to gain insight in the processes and identify the technology challenges. We apply innovative ideas to overcome these challenges and towards the end develop sustainable solutions for our clients. With this approach, we have been providing end-to-end process engineering solutions to our clients in various domains such as chemicals and processes, consumer goods, oil and gas, power generation, and pharma. Today, our team consists of around 60 plus professionals, PhD and master's degree in various engineering domains. If you look at our solutions portfolio, we started out as a CFD modeling and simulation company, and over the last decade, we have handled a wide range of complex systems using some state-of-the-art tools and CFD software. Over the last decade, we have also expanded into different domains. Discrete element modeling is one of those fields which deals with granular flows, and we study systems such as flow of particles, tablet coating, and so on. We also have an experimental lab which specializes in building custom experimental setups and houses some state-of-the-art instrumentation. Software development team of Tri-Diagonal is customized software development as well as GUI and vertical application development. We also have a process engineering division which provides process engineering services wherein we design and build pilot plan for our clients. This is our flagship product, Mixit. Mixit is a stirred tank optimization tools that allow you to perform correlation-based as well as CFD-based analysis of stirred tank. One of the key features of Mixit is CFD is fully automated in Mixit, and so even the users with no specialized training in CFD can perform the analysis. So, proceeding with today's webinar, I would like to introduce you all to today's speaker. Our speaker for today is Dr. Gopal Kasat. He's PhD in Chemical Engineering from Institute of Chemical Technology, Mumbai. He currently heads our Chemical Reactor Engineering group, and he has been with Tri-Diagonal since last 8 years. His group mainly focuses on design of multi-phase reactors, chemical reaction and reactor engineering, multi-phase flow characterization using EFD, CFD, and so on. With that, Dr. Kasat, I would like to invite you to start our today's webinar.
Thank you, Amaya, for a very good introduction. Good morning, everybody. Let's start discussing today's topic, which is how we can do good scale up, good design of your mixing processes, and how we can take good control over those mixing and scale up issues so that the product properties which we get out of our vessels meets our requirements. So let's start understanding what is mixing in process industry. So in every process industry, what we are trying to do is we are trying to convert the raw material into a value added product, and this we do through some of chemical or physical transformation. In each of these transformation, if we look into detail, mixing is one of the most important unit operation. We are either bringing two different liquids together, or we are trying to disperse gas in liquid, or we are trying to suspend solids in liquid. So what we are trying to do is we are trying to reduce the inhomogeneity either in concentration or in phases or in temperature. And what we are trying to achieve is the desired process results, which needs efficient mass transfer, heat transfer, and good reaction rates so that we can get good conversions and selectivities and well-defined product properties. However, if we ignore the mixing quality and the mixing performance of the vessel, then because of poor mixing performance, these are some of the numbers which are reported in the literature that you get low yield and poor selectivity in chemical when we are talking about chemical reactions. Wide particle size distribution, if we are talking about crystallization and polymerization processes, then we can get very wide particle size distribution, which can impact our product properties. Similarly, when we are talking about bioreactors, where we are distributing gas in liquid, we can get non-uniform gas distribution, which leads to inefficient performance of the reactors. So there are many different impacts of the poor mixing, and that's why we should be making sure that we are doing right scale up, right design to address all our mixing issues. So let's try to understand what are the rules to do this scale up or these designs. So typically I classify or I define this rule based on the processes. Uh, let's say we are trying to mix two different miscible liquids. What we should be looking at is the equal blend time. That is, what is the blending time in a lab scale or what is the blending time in a pilot or plant scale reactor. If our application includes suspension of solids, then we should look at the suspension of solids from the vessel bottom, and one of the critical parameter to look at there is NGS. So if we are trying to match the suspension quality between the lab and the plant scale, we can get equal mass transfer rates from solid to liquid, and we can get our desired product properties. Similarly, for gas liquid systems, we typically use the rule of equal mass transfer coefficients, which again depends upon the power dissipated in the system, power per unit mass or per unit volume of the liquid volume, and gas buildup and mass transfer coefficients in those reactors. For heat transfer control processes, we should be looking at heat transfer rates, which are again controlled by the heat transfer coefficient. For fast reactions, micro mixing time is one of the scale-up parameter which we typically try to match between the lab and the pilot or plant scale facility. For liquid dispersions, we typically look at the shear rate distribution, and again, which is again depend upon the power per unit mass. So there are many different parameters which we typically look at in each of these different applications, like liquid blending, solid suspension, gas dispersion, heat transfer applications, and liquid dispersion. These are the various parameters which we look at when we design or scale up our vessels or the processes from pilot to plant, or we transfer the processes from one plant to another plant. We typically look at matching these parameters between the two vessels. We understood now what are the rules which typically the process engineers looks at when they scale up. Now let's understand what are the variables available to us which we can vary to attain these mixing parameters. First and foremost, I typically classify these into two different classes. That is, one is the reactor parameter, which are reactor related to reactor design, so reactor hardware we can call them, and another are operating conditions which we can control by controlling various different parameters. So many parameters that like various tank shapes are available. We have many times spherical, round bottom flask in the lab, and we are trying to scale them or equate them with a cylindrical vessel in the pilot or a plant facility. Similarly, many different impellers are available, and we have to select which type of impeller should be used for which type of application. We have axial, radial, and mixed flow impellers. We also need to decide what should be the size, number, and location of the impeller. how many numbers of impeller to be used, and where those impellers should be located in the vessel. We also need to look at what amount of baffling we are providing to in the vessel, which also controls to a great extent the degree of mixing in the vessel. Internals like coils and dip tubes may act as a baffle many times. We may not have baffle in the vessel, but we have some dip tubes, some probes inserted in the vessel, which acts as hindrance to the flow, and those also need to be accounted when we estimate our mixing parameters. We can control the process of mixing by changing the impeller speed, which is our operating parameter, and we can also alter the heat transfer rate by controlling the heat transfer coefficient or the flow of fluid through coil or jacket, which we are using as a heat transfer medium. For crystallization type of processes, when we are adding a second solution or an anti-solvent, which typically we want to distribute it very quickly in the reactor in the reaction volume, we try to alter the feed rate based on the mixing capacity of the vessel, and that also becomes one of our controlling parameter to control the product properties. So we looked at the design variables. Now let's look at what are the design methods available to us which we can use to come up with the scale up or designs of the mixing vessels for our requirement. I typically classify them into 3 different classes, and let's go through each one of them. So level 1 methods are general design guidelines, thumb rules, which we may have been picked up from literature, or we have available knowledge base as a corporate. So many different organizations may have their own knowledge base, and we also collect these thumb rules or develop these thumb rules based on our experience of designing or scaling up various vessels for various applications. Some of these rules are listed here, which all process engineers generally use. So let's say if we are looking at a miscible mixing of miscible liquids, what typically we are looking at, mainly we need much flow and motion of the fluids so that the 2 different liquids can be mixed. Similarly, for solid suspension, we need a lot of flow so that that flow can suspend solids in the vessel. In these applications, typically axial flow impellers will help us to get more flow at less power consumption. And then if we need to get good flow patterns, we should restrict the impeller diameter to be equal to or less than 50% of the tank diameter. The impeller diameter should not exceed typically 50% of the tank diameter. If we have very high viscosity fluids, then we can look at use of anchor or helical ribbon impellers. There are some guidelines or thumb rules available to decide where the impeller should be located from the vessel bottom, or if we are using a multiple impeller system, what should be the spacing between the impeller. So we can look at the 30% of the tank diameter, the distance from the bottom of the vessel for the impeller. And if we are using multiple impeller system, then we can space them. The spacing between the impeller can be equal to the impeller diameter. For solid suspension, we generally provide a very small tickler impeller at the bottom so that it keeps the solids suspended from the vessel bottom. Similarly, there are rules available or thumb rules available which we can use to decide on what number of baffles to be used. Similarly, we can, for mixing of miscible liquids, immiscible liquids, where we are talking about processes like we are dispersing one liquid into another, liquid-liquid dispersion, as well as gas-liquid mixing, we need flow plus we need shear. Shear we need because we want to disintegrate the second liquid or liquid to be dispersed or gas to be dispersed into finer droplets or bubbles, and for that we need high shear impellers. So the impeller which gives us more power dissipation need to be used in those applications so that we get high shear, which can give us finer droplets or finer bubble size so that we can enhance our mass transfer rates. We can use those impellers in combination with axial impellers so that it gives us flow, so that we can distribute these fine bubbles or fine droplets evenly in the tank volume. Then there are various different guidelines available to select from the Sparger diameter, and you can look at those guidelines here. Similarly, there are guidelines available to select how many number of impeller to be used based on the liquid height to tank diameter. Let's look at the level 2. So these are level 1 methods. Let's look at what are the level 2 methods. So in level 2, we typically use empirical correlations, which we are using to estimate our various mixing parameters. So let's look at the first application, which is mixing of miscible liquids, and we are trying to look at here what is our blend time, or what is our scale of agitation. If we look at all these correlations which are available, we will notice that one of the important parameter in all this is the impeller power number. So the correct estimation of impeller power number or the flow number is very critical, or the correct availability of this number, correct number for our application is very critical to get accurate estimation of what is the blend time for our vessel. Similarly, if you look at solid suspension applications, we have equations available to calculate the critical impeller speed for off-bottom suspension. I have listed two different correlations. One is the very old and widely used correlation proposed by Swettring in 1958, and one is the recent correlation proposed by Professor Greenville, which is published in 2015. And if we look at these two correlations, we see that in the Swettring correlation, impellers, the S factor is a critical parameter which can decide how we calculate the NGS and what is the NGS number for our vessel. And in the Greenville correlation, we again look at power number is a critical parameter. If you look at this S factor, we get that there are these S factors are different for different impellers. So again, good estimation of this S factor or the impeller power number is very critical to get good predictions or appropriate predictions for the critical impeller speed for a given application. Again, in solid gas liquid mixing, if you look at the scalar parameter, we typically look at power consumption, power per unit volume, gas held up, and mass transfer coefficients. And these are the typical type of correlations which are used to estimate the power consumption, gas hold up, mass transfer coefficients, and even the bubble size in a gas liquid application. Again, we look at the power number as a critical parameter. So power number, based on power number, we will estimate the power consumption, and that power consumption is used in various different equations to estimate gas hold up, mass transfer coefficients, as well as the bubble size. So again, power number became the critical parameter in all these correlations to be used. Many different correlations are available to estimate gas hold up, and these constants over these equations vary as per the different impeller or different combination of the impeller if the system is a multiple impeller system. And there are various literature reference available from where we can select this from. For fast reactions, again, we are looking at micro mixing time, which is again depend on the power consumption. The energy dissipation rate is again depend upon the power consumption. Again, impeller power number becomes a critical parameter. Similarly, for liquid dispersions, we can look at the shear distribution or shear rate. And if we have to estimate the shear rate, again, we typically use the Meissner-Otto equation to estimate the average shear. Again, there is a Meissner-Otto constant, which is again depend on the type of the impeller which we are using for our application. And these parameters are available for few impellers and not each and every impeller. So to summarize these level 2 methods, we can say that these all correlations heavily depends upon the impeller characteristic to be accurately estimated. And these impeller characteristics include power number, flow number, the S factor for NGS calculation, Meissner-Otto constant, and various constants used in the gas hold up or gas liquid mass transfer coefficients. And correct estimation of these impeller characteristic parameter becomes very important for applying these correlations to the system of interest. We need to know all these parameters appropriately or accurately for our system so that we can get good estimation of our various mixing parameters. And how we can get what these numbers depends upon. So let's look at the power number and flow number. This power number and flow number of an impeller will change based on the typical regime of flow regime, that is either we are working in laminar transition or a turbulent flow regime. So power number typically decreases and becomes constant in a turbulent regime. So the power number depends upon the impeller type. What is the type of impeller? We can look at various different impeller types have different power numbers. It depends upon the Reynolds number, which is we can say based on the viscosity. The number also depends upon the impeller diameter to time diameter ratio, impeller clearance to time diameter ratio. Similarly, if we are operating the impeller as a single impeller or if we are using multiple impeller system, the power number varies for those applications. and the power number estimated when the impeller was acting as a single impeller may not be applicable when it was acting as a multiple. Similarly, power number estimated for a typical D by T ratio may not be applicable for a higher or a lower D by T ratio. So we need to account for impact of all these parameters like impeller spacing, liquid level, degree of baffling on the prediction of impeller power number and flow number so that we can get accurate estimation of our mixing parameters. However, so if we have to summarize these two methods, the level one, these are general design guidelines and the thumb rules, and the level two methods, which are empirical correlations, which are these numbers are typically derived from empirical or experimental data. These correlations are derived from experimental data, and if you look at the uh, positives of this, these are quick design methods and gives us reasonable accuracy for standard system because all the impeller characteristics are available, fairly available with decent accuracy for all standard systems and standard configuration. However, if you look at the other side, we see that these correlations provides us average information and they are heavily depends upon the impeller characteristic, the flow number, power number, or various different constants which we want in various different applications. Similarly, if we look at the literature or many data available, we see that these correlations are supported by limited experimental data, and when it comes to non-standard configuration, some of the example I'm showing here, then we have very less information available even on the basic impeller characteristic like flow number and power. So in these case or in such conditions, we may not be able to use the empirical correlations with full accuracy to estimate our mixing parameters. So what are the alternatives available to us? So in those systems where we do not have the data available, we can go and build those systems and perform experiments, and we can use various different experimental techniques to measure various parameters like velocity, power consumption, gas distributions, distribution of solids concentration using various different experimental methods. However, if we look at these measurements and kept performing these measurements, this becomes very expensive because we need to create a prototype and perform a lot of tests either with some dummy materials or with actual materials. So this can be expensive and time consuming and can impact our time taken to take the product to the market. So do we have any alternative methods? So yes, we can use the numerical experiments very similar to what we perform the actual experiment. So we call it computational fluid dynamics, similar to experimental fluid dynamics. So we are doing some computer experiments, numerical experiments using CFD models to understand what could be the performance of our vessel. These methods, computational fluid dynamics methods, gives us quick solutions to build quick understanding and build various different analysis for different design scenarios, and they typically provide us very detailed information. We can get detailed local information or estimation of velocities in the solution domain, and we can handle with these non-standard configurations as well. So we may not be limited to standard systems in these applications. So let's understand what does CFD analysis and what does it require to perform a CFD analysis. Let's look at it from a stirred tank perspective. So there are different steps available in the CFD analysis. So we need to create first the 3D CAD model of our system, and then we need to discretize the domain into number of cells where the competition will happen so that we can get 3D variations of the various mixing parameters. While we perform the machine operation, we need to make sure that the machine has appropriate cell count in the region where we have high velocity gradients and where we can use some coarser mesh where we have low velocity gradients. So all these care need to be taken while we perform the machine operation. So once we do the machine, we need to provide all different fluid properties, boundary condition in terms of impeller speed, and the typical different boundary conditions at various domain extents. And then we can solve these equations in an iterative manner. We need to make sure that we are converging the solution appropriately, and then we need to extract the results to get our various mixing parameters. So we need to get expertise in doing all these different steps so that we can perform a decent CFD analysis. Let's understand what these CFD analysis can provide us when it comes to stirred reactors. For stirred reactor, we can get the detailed impeller characteristic, like we can estimate the impeller power number, flow number in detail, and then maybe we can use this impeller characteristic in combination with some of the correlations to get more estimation from this analysis. We get detailed flow patterns, we get mixing profiles. You can look at it. Some of the examples I am showing here. That you can get the flow patterns in the vessel. We can get velocity distribution. We can get dissipation, energy dissipation rates at different locations in the vessel. What is the energy dissipation rate near the impeller, away from the impeller, near the baffles? We can get detailed estimation of that. We can get distribution of shear rate, and if there are liquid droplets, we can understand by using various methods that what amount of time those droplets or those bubbles spend near the impeller and away from the impeller. So that will help us to characterize how much time those droplets, solids, or the gas bubble spends in the high shear as well as low shear zone. That helps us to characterize their particle size distribution in a given vessel. Similarly, for gas liquid distribution, we can get gas buildup, gas distribution, gas concentration distribution, and mass transfer rates. We can get estimation of the vortex depth and gas entrainment from the through the vortex, typically in case of applications like hydrogenation processes and different systems. And we can get even solid distribution profiles using the CFD analysis. So we understood that how we can use CFD analysis to get various mixing parameters. Many times we use CFD analysis to characterize the impeller as well. So let's say we have a new impeller, we can build some standard models using some standard configuration and perform simulations at various different Reynolds number, estimate the variation of impeller power number or flow number as a function of Reynolds number, and then digitize this curve into using some of the equations. You can use various different forms of equation so that you can use these equations along with your correlation to estimate your mixing parameter. So if you look at all the correlations which we have discussed, estimation of power number and flow number is a critical parameter. So we can run a bunch of CFD simulations and characterize our impeller to get the estimation of power number and flow number, and then use that in our correlations to estimate various mixing parameters. So with this, I complete introduction of what are the different scale-up rules, then what are the design variables, and what are the design methods available to us. Now let's look at how we can apply these design methods to solve various problems at our hand. And in next few slides, I will go through some of my experience during the my tenure at Tridiagonal Solutions, or my PhD work during my PhD, that I come across, and I use various these design methods to address mixing and scale-up problems for various of our clients. So let's look at very simple application that we are trying to design a system which will give us a mixing time similar to what we have observed in a lab scale vessel. That is, let's say the mixing time required is 10 seconds. So we know that we need a mixing time of 10 seconds, and we know the react volume of the liquid to be mixed. Based on that, using our thumb rules, we come up with a system that we need an axial flow impeller with minimum power and maximum flow, and we select the impeller diameter based on the standard rules available, that is impeller diameter to the tank diameter ratio of 30%. Similarly, the clearance, we decide where to locate the impeller, and we use standard baffles in this application. Now we use correlations and we estimate the mixing blend time, which comes out to be 8.2 seconds for this specific condition. And if we have tried to measure this with the actual system, and the correlation based predictions for such a standard system match very well with the measured blend time, which is about 9 to 10 seconds. And we can use this correlation to estimate blend time at various different impeller speed, and then we can optimize which impeller speed to be used to match the required blend time of, let's say, 8 to 10 seconds. So here, what I'm trying to highlight is that for standard system, you can confidently use or very safely use correlations to get estimation of your mixing parameters. Let's look at the second application, which comes from one of our experience with consulting projects where we are trying to troubleshoot issue posed by our client. So the problem was the vessel was giving required productivity when there was a particular batch size. Now, because of some requirement, the batch size was slightly increased. The impeller spacing, you can look at the typical impeller spacing, which was with the original batch size. The batch size was slightly increased here. And with this increase in the batch size, there was the problem with the product quality was observed, and it was thought that it can be a mixing issue. Let's look at if the correlation can provide us some more insight, we can use course. So we have understood, estimated using the correlation blend time, and we looked at the mixing time is very similar to for the increased batch as well as the original batch. There is a very slight difference. However, the product qualities were varying very greatly. So this correlation was not able to explain us why there is such a large difference between the product quality by changing by changing the batch size by a small amount. So let's see, can we use, as we discussed, that can we use the level 3 methods as CFD models to get more insight into this problem. So we build CFD model for the multiple impeller system. We use the typical different meshing applications, and we understood that this is the original batch, this is the flow pattern in the original batch, and you can look at the velocity distribution in the increased batch. This detailed analysis provides us that there is a low velocity zone near the top, which might be impacting the mixing performance of the vessel because of the increased batch size. Now let's look at more deeper insight. Can we understand how is the mixing happening for a tracer added or for a chemical added near the vessel, near the fluid surface? So we simulated this, and we then understand that in the original batch there was a good mixing. However, in the increased batch, you can see the dead zones even after 19 to 20 seconds. However, in the original batch, the blend time was about like 15 to 16 seconds. However, with the increased batch, the blend time is not 15 seconds, it is more than 15 seconds. Like we can look at, and we can see that it is about more than 25 seconds. So how to improve this? Now let's look at how we can improve this. One of the quick suggestion or quick look at this is let's change the impeller spacing. But what should be the impeller spacing? What is the optimum impeller spacing? And let's look at, can we again get CFD methods to look at this? So we looked at two different options. One is keeping the impeller spacing same and just moving the whole impeller system a bit towards the liquid surface. And another option was having good different impeller spacing over the reactor volume. We looked at the flow distribution because of these two different impeller spacing, and you can look at that with the option 1, where we have spaced them widely apart from each other, the top impeller is acting as a separate impeller, and there is a separate circulation loop formed, and there is a disconnect between the flow loop formed by the top impeller with the bottom two impeller. However, in the second option, we can see that there is the good interaction between the three impellers, and we can find a good one single circulation loop, which may give us good mixing. Let's look at if the mixing is improved with the two different options. So with the base options we were looking at the mixing time of about greater than 30 seconds. However, with the different impeller spacing, we are looking at a mixing time of about like 16 seconds, which is what we desired with the original, which is in comparison with the original batch. So the objective of this example, to demonstrate this example, is to demonstrate how we can use this detailed CFD analysis to get more insight into our vessel performance, and appropriately correct the design or correct the operating conditions so that we can get the desired mixing performance for a given system. Another example is from one of the experience with the tech transfer applications where uh, the the application was of a suspension polymerization process, and the requirement was a particular particle size distribution which was observed at the lab scale. So the lab scale was tuned to get the desired particle size distribution. Now the options, two options were available to transfer the batch in a plant from lab scale to pilot scale. In a lab scale, a typical anchor type impeller was used, and then there were two different options. Should we use anchor impeller or should we use a three impeller system with a hydrofoil impeller? Let's look at how we can get more insight into this. How to predict which one gives performance similar to a lab reactor. So we try to understand the shear distribution and based on the correlations and the Mesh-Norton constant, but that did not give us more insight. Then we are trying to look at can we use CFD methods to get more insight. Now we are talking about a suspension polymerization process. This typical process, we are looking at particle size distribution, and we know that particle size can vary if the particles spend very large amount of time near the impeller and if they spend a different time or a large amount of time away from the impeller. If they spend more time near the impeller where the shear rate is very high, the particle can break into smaller particles and we will get fine particles. If they spend more time away from the impeller, then we will get coarser particles because they are spending more time in a low shear zone. So let's see if we can characterize these shear distribution of the particle using the CFD method. So we did perform the flow simulation and then track the particles, and then we understand their shear exposure history, how much time they spend near the impeller and how much time they spend away from the impeller. So if we look at the percent time spent by the particles and if we compare them between the lab, the red indicates the green indicates the lab, the red indicates the with the hydrofoil impellers, and the blue indicates with the anchor impeller. And we see that the option 2, which is with the hydrofoil impeller, matches very well with the lab. So the shear distribution history, exposure history experienced by the particle, we were able to match between the lab and the option 2. When we actually perform experiments on the option 2 and option 1 as well, we see this is the distribution of particle size for the option 1 and option 2 where the shear distribution history was matching, we get matching performance or the matching particle size distribution compared with the lab reactor. So with this we can say that if we get more detailed insight into the performance by using the shear exposure history of the particle using CFD models, then we can get better understanding of the vessel performance and we can select which vessel to be used to transfer our batch. So all through these three examples, what we are trying to see is that for simple applications and standard configuration, yes, correlations will work good for us. However, when it comes to more detailed insight so that we can improve our process much better, we need to get better insight into the vessel performance using advanced techniques. One more application we would like to quickly highlight is getting a scale up right. The application was hydrogenation. This was the lab vessel where a pitch blade turbine was being used and the conversion was about, let's say, X%. When this batch was transferred to a 1 kiloliter vessel, the conversion was only 30% of what was observed in the lab scale. We try to understand using correlation what could be the reason behind that, and we understood that the power per unit volume is very low in the large scale vessel compared to the lab scale vessel. So what could be the different scenarios we can do to increase the power per unit volume? One is that we can increase the impeller speed to get more power dissipation. However, if you look at the application, it is a hydrogenation process and corrosive materials are involved. That's why the glass line reactor is used. And as soon as we use the glass line reactor, we get limits on the impeller speed. We may not go beyond like 90, 96 RPM for a 1 kiloliter scale vessel. So we cannot have much improvement in the performance by changing we were already operating at the limit of the impeller speed. So let's look at what we can do to get, we looked at the performance and we see that the hydrogen getting entrained in the liquid, we use CFD models using multi-phase models to get that how is hydrogen getting entrained, and we see that there is a good amount of hydrogen dispersion in the lab applications versus the pilot system. So the reason can be poor conversion will be the low entrainment of hydrogen from the large scale and its distribution in the vessel as well because of the low power consumption. Let's look at, can we do some scale up designs and arrive at a good better scale up using correlations as well as CFD models. So we looked at how we can improve the power consumption because we do not have much flexibility on changing the impeller speed. So we looked at, can we use different combination of impellers to get the more power dissipation in the system and better hydrogen entrainment from the liquid from the top headspace. We looked at multiple different options, and CFD helped us to gain quick analysis of this using multi-phase models to understand the entrainment of the hydrogen from the headspace and the distribution of hydrogen once it is entrained in the vessel. So CFD gave us some better insight into this. We looked at the different designs and looked at the power per unit volume of these different designs, and we see that for all these designs we have a better power per unit volume. Similarly, we have better gas liquid interfacial area as well, so we have improvements. We can select any of this design. However, design C was selected in discussion with the plant team of our client because it was easy to fabricate and the fabrication cost was low in this system. We perform many different batches with the third design, and we see that we get threefold increase in the conversion levels with the modified design. So the conversion was improved from 30% to 83% of the lab when we use the improved design. Again, the objective here to show that for some applications we need to get more detailed insight into the performance, how we can entrain the hydrogen in the heads from the headspace through vortex, how we can control the vortex, how we can control the hydrogen entrainment, and what different options are available to us, and how we can estimate which options will give us better performance, and we can use CFD models or advanced models to get this better insight into the vessel performance. One more application I would like to quickly highlight is of a hydrogenation of aerobic fermentation, where standard guidelines were used to design the fermenter, one high shear impeller near the sparger, so that whatever the gas comes from the sparger is quickly disintegrated into finer bubbles, and then axial impellers were used to provide to distribute these bubbles quickly over the reactor volume. We used correlation to estimate gas buildup and mass transfer coefficients, and they were very well with the experimental and the predicted. However, still we seen the client was experiencing a poor performance for the aerobic fermentation system. We used CFD models and looked at the detailed performance using flow patterns and gas distribution, and we can see that there is a disconnect between the flow patterns of the top and the bottom two impellers, and because of this there is a non-uniform gas distribution as well as mass transfer distribution across the vessel volume, and this was impacting the performance of the microorganisms which are involved in the aerobic fermentation. And because of this, in some region oxygen was not available to the microorganism, and because of that we were getting non-uniform performance or poor performance for the fermentation application. Similarly, we can use this detailed model to understand for non-standard system where your impellers are angled or off-centered, where the correlations are not available. We can see which impeller to be selected and where the solids will be uniformly distributed over the reactor volume. We can look at one more application I would like to quickly highlight is the dispersion of powder from the floating powder or the light powder from the liquid surface. We had a system where the up pumping impellers were used, and if we looked at the detailed performance, and we seen that there is a secondary circulation loop being formed near the liquid surface, and because of this the powder dispersion was not uniform or not getting properly distributed. Whatever the added powder at the liquid surface was not get uniformly distributed. So we understood the reason, then we tried to understand, can we improve this by changing the impeller speed, so we can look at the detailed performance using CFD. We see that there is an improvement in the flow pattern. Can this gives us improvement in the power distribution? So changing impeller spacing led to a better powder distribution for a floating powder. So this is how we can use these models to get more insight and design our vessels or impeller systems properly to get the desired mixing performance. Similarly, we can use these CFD models to get complicated performance for complex systems like coaxial counter-rotating impeller, where there is very limited, or we can say no correlations are available to estimate the power consumption or the velocities, average velocities, or shear distribution in this vessel. Here, we can use CFD models to get detailed understanding of the flow pattern, impeller power characteristic, the power number, phone number, power consumption, as well as the shear information near and away from the impeller. So to summarize my discussion today, I would like to highlight some of the points that multiple methods are available to address our mixing and scale-up issues. Level 1, Level 2 methods, which includes general design guidelines and correlations, can give us better control or better understanding for standard systems. However, these have limitations when it comes to non-standard or complex applications or complex processes. We can use experimental methods for such complex processes or non-standard systems, but this can be expensive and time consuming. Alternative is we can use computational fluid dynamics based models to get more detailed understanding of the flow distribution and mixing performance in our vessel. And these systems, as we can see from various applications, have great potential in getting more detailed insight into our vessel performance. And this can reduce uncertainty in our design, scale up, or tech transfer from the lab to the plant, and can reduce our time to the market. So let's understand, if we have to do detailed CFD analysis for some of our applications, what are the options available to us? Number of CFD tools are available in the market, commercial as well as open source. We need to get expertise in performing various steps, like we need to get expertise in creating the geometry, performing the meshing application, and simulation. And this can be sometimes time consuming, looking at the busy schedule of a process engineer, as he needs to also look at various different objectives of his to perform on his for the scale up. So do we have any tool available so that we have the we can automate this process of a CFD analysis, and we can get some quick simulations done, and we can understand the performance in more detail, and we can use these complex methods in an automated way. With this, I would like to quickly introduce, as Amaya highlighted, that we have developed a tool, we call it Mixit, which gives you opportunity to use correlations as well as the higher level CFD models to understand the detailed mixing performance of the vessel. We have developed this tool with a vision that it will help chemists and process engineers to accelerate their scale up and tech transfer and connect dots between the reactor and process attributes using both empirical correlations and advanced CFD models. These are the various features available in the tool. And with this, I would like to conclude my talk today. And we thank you for your attention, and we are open to take any questions from all the attendees.
Thank you, Dr. Kasit. We are now going to begin answering the questions that were submitted during the presentation. As a reminder, you can still submit the questions through the questions pane in the attendee panel. So, Dr. Kasit, the first question is regarding scale-up. Mixing units at production scale are usually not geometrically similar to the laboratory or pilot scale.
Correct.
And the question is how scaling of problems should be addressed when there is no geometric similarity.
Yes, so typically we look at many applications today and some of the examples through the discussion that there was no geometric similarity between the lab. We have a lab vessel where we have round bottom flask and we have a cylindrical vessel to be for the batch to be transferred in the plant scale. In such systems, we may or may not be able to use the correlations because the details, as we see that power number and flow number are not available. In such applications, we can perform few simulations to understand the performance and make sure that we are getting the similar mixing performance, or we tune the parameter to get the similar mixing performance, and then transfer our batch from the lab to the plant or the pilot scale.
Okay. So the next question is, how do you generate the NP versus RE curve, and how many simulations are typically required to generate that curve?
Okay, so let me go back quickly to the slide. To answer this question, so this is the curve which we need to generate, and typically any curve fitting will need at least 5 points so that the curve fitting is good. But looking at the complex shape of this curve, based on our experience, we can say that 3 points in the laminar regime, 3 to 4 points in the transition regime, and 3 points in the turbulent regime will be good to represent this curve. So in total, we can need 10 simulations to represent this curve to develop the NP versus RE curve.
So we are done with today's questions. I would like to thank Dr. Kaset for presenting us with today's webinar. If you have any other questions, please contact us at info@tridiagonal.com. You will receive a follow-up email within 24 hours with a survey. Please fill in the survey to give us the feedback on the webinar. On behalf of Tridiagonal Solutions and our presenter, thank you for joining us today, and have a great day ahead. Thank you.
Thank you all for your attention. Thank you.